Hello everyone, I'm Paloma Sori from Carnegie Mellon University, and I'll be presenting our work on incremental constraint smoothing for state estimation. So let's begin by looking at the state estimation problem in robotics. Typically, we formulate estimation problems as smoothing problems, where the goal is to estimate the most likely states given a stream of measurements. So for instance, consider this tabletop manipulation scenario where we have a robot arm pushing around an object. The robot cannot see the object pose directly, but only sense it through contact measurements. The goal then is to estimate the pose of the object using a stream of these contact sensor measurements. However, in robotics, estimation goals are not in isolation. Estimates returned from the estimation module are in turn used by downstream components such as a planning module. And such planning modules typically reason about a model of the world with physics and geometric constraints. Now, if estimation is agnostic to these constraints, it may end up sending implausible estimates to the planner, which would break these physics and geometric assumptions that are made by the planner. Hence, we look at the problem of enforcing these constraints on the estimates. We consider both equality and inequality constraints. For example, a gripper pushing an object induces equality constraints. A robot navigating within a corridor must satisfy inequality constraints. So let's formalize our problem. We formulate the problem as a maximum a posterior estimation of states given all measurements until the current time step. Here, X is that sequence of states, such as the object pose in the manipulation scenario or the robot pose in the navigation scenario, and phi is the likelihood of obtained measurements. We represent this problem as map inference over a factor graph, where the variable nodes are the states that need to be estimated, and factor nodes encode the measurement likelihoods. Under Gaussian assumptions and linearization, this results in an unconstrained least squares objective that must be solved in every iteration. So we now introduce constraints as equality factors in red, represented by the G matrices, and inequality factors in orange, represented by the H matrices. And this is the constraint subproblem that we must solve for every iteration. So as for related work, we can organize the related work along two axes. Within the framework of batch factor graph optimization methods, there has been work in looking at both unconstrained and constrained methods. We are interested in an incremental setting where a robot is constantly receiving measurements as it explores the environment and must efficiently update its state estimate. ISAM, as introduced by Case et al., provides a way to solve the problem incrementally for an unconstrained optimization objective. So in this work, we extend these incremental approaches to now also be able to solve for a constrained optimization objective. And our key idea is to leverage primal-dual methods, in particular the Augmented Lagrangian, that solves this problem as a two-player game. So in the purely unconstrained case, we have only a single player, the primal solver. It solves for an unconstrained nonlinear least squares objective that we saw earlier with variables delta x. And we know that we have good solvers for doing this efficiently, such as ISAM that uses sparse incremental Gauss Newton methods. Now, when we have constraints, we need to introduce dual variables, v and u, that would ensure that the gradient at the constraint optima would be exactly zero. So the dual variables here can be thought of as knobs controlling the constraint term contributions to the gradient terms. Hence, we need a second player, the dual solver. So we can now think of this as a max-min game. At any given round, the primal solver solves for delta x, keeping the duals v and u as constant. Once the primal returns its solution for delta x, the dual solver now solves for v and u, also called Lagrange multipliers, keeping the primal delta x constant. And this happens iteratively until a convergence criteria. And the advantage to doing this over other methods such as active set or interior point is that we retain the benefits of primal optimization by continuing to solve for an unconstrained quadratic in the primal step. We can hence use sparse incremental Gauss Newton methods for the primal optimization, while the dual optimization is simply a first order gradient ascent. So let's briefly step through the algorithm. In the unconstrained case, since our original matrix A is sparse, we can solve for delta x efficiently using a square root factorization. Here RT is that upper triangular square root matrix at time step t. Now, instead of recomputing this factorization from scratch every time step, existing work, that is ISAM, computes this efficiently from the previous factorization via Gibbons rotation. And this forms the basis of our primal solver when doing an incremental constraint update. So we now return to the constraint framework where we had both primal and dual solvers. And we introduce new matrices G and H that are coming from the constraints. The primal equations now involve a forward and a back substitution step. The dual equations involve a gradient ascent step, and the primal dual steps are repeated iteratively until convergence. So now let's look at some experimental evaluation. We evaluate our method on 3 different datasets, applying equality and inequality constraint factors as shown in red and orange. We evaluate against an unconstrained baseline that applies the same factors in red and orange as unconstrained factors.
In the contact dataset, we model contact measurements as equality constraint factors in red that constrain the squared distance between the object and the gripper. Here we visualize qualitative results along with constraint violation and error plots. And we can see that the constraint solutions in orange are able to satisfy the equality constraints more precisely than an unconstrained solver solutions. In the navigation dataset, we apply inequality constraint factors in orange that are piecewise linear constraints corresponding to boundaries of the corridor that the robot is in currently. And here we again visualize the qualitative results along with constraint violation and the error plots. And we can see that the incremental constraint solver in orange satisfies constraints by keeping the trajectory estimates within the corridor boundaries at all time. And what you see in green are the corridor boundaries being plotted that correspond to inequality constraints operating on the current robot pose. And here we show other points in the trajectory where the inequality constraints are able to keep the estimates within the corridor boundaries. Finally, we show that the violations for the constraint solver in orange are invariant to the weights of the corresponding costs in the objective, which would not be the case with a purely unconstrained solver. And this invariance occurs since the dual solver is able to adaptively vary the dual variables to ensure that the gradient goes to 0 at the constraint optima. So in summary, we looked at the importance of constraints in estimation and how to leverage primal-dual methods for solving them incrementally. As a result, we were able to satisfy hard constraints precisely within a threshold without having to recompute solutions from scratch. As future work, we have been looking into improving relinearization and runtime performance of our approach. Thank you so much for your time.